Welcome, students and listeners, to the fourth iteration of the lecture series on medical imaging systems that covers mostly about the tomographic techniques. In my previous lectures, I briefly talked about the basic computer tomography techniques, imaging systems, different applications of computer tomography, as well as the modern developments or the state of the art techniques that has been used during the CT scan. So in this module or in this lecture, I'll talk about a very important development, a very important improvement of tomographic technique that is known as microcomputed tomography, or in simple way, or in short form, micro CT. So the to understand micro CT, we need to understand why this tomographic technique is very popular and why understanding the concept of micro CT is very important. To begin with, the micro CT, first, the most important aspect of micro CT, it's a non-destructive imaging technique. So what is a non-destructive imaging technique? We can visualize the internal structures of, of any objects without destroying that object or without cutting or slicing that object. That's what we is known as a non-destructive imaging. And micro CT is predominantly used to non-destructively image not only biological system, biological research related uh, systems, or it also used for imaging material science related different objects, be it composite, be it any other objects. So micro CT is a non-destructive imaging technique, which is again like a regular computed tomography, uses X-ray to create a detailed 3D image of the internal of an object. Another, apart from being a non-destructive one, micro CT is also a high resolution imaging modality as compared to the conventional CT, that is particularly well suited for studying the internal morphology of, as I said, not only for biological specimens, biological objects, as well as for other material science related objects, that is non-biological, particularly for small objects. So why is this city called micro city? Sorry. So the prefix micro essentially indicates that the pixel size associated with the voxels in that in any object of any cross section area are in the micrometer range. That is typically belong to 1 to 50 microns, and that this micrometer range of the pixel sizes actually makes the micro CT capable of capturing images at a very high resolution. Therefore, the most important points of micro CT is that it is a non-destructive imaging technique, not only for biological systems, not only for biological objects, specimens, but also for specimens related to material science or metallurgical engineering. And generally, the objects that are being scanned using micro CT are relatively smaller objects as compared to those scanned using computed tomography or conventional CT. The second thing is that it is called a micro CT because the pixel size of any cross section image are in the micrometer range, typically within 1 to 50 microns. That makes micro CT capable of capturing images at a very high resolution. We can see, to understand why micro CT is so important and what this micron level imaging pixel size can offer, This is a imaging microcity based image of a single leaf. We can see this through this video the basic detailing of the that microcity imaging modality can capture. So here we can see the minute details, the intricacies of a single leaf, which is very thin, and just because of the micron level pixel size, it can produce more detailed image at a very high resolution. As we can see, each and every veins of this leaf can be seen with much with intricacies, which higher details. So the next and perhaps the important question after coming from conventional CT, why should we use microcity? So in medical imaging, particularly in case of radiological images, high resolution is of utmost importance or is particularly very essential for accurate diagnosis. So higher resolution images can provide, as we have seen from the previous slide, that the higher resolution of that image can provide a clearer visualization of the intricate details of a leaf, which is a very thin structure. So it can be well understood that the images thus formed from microcity can provide clearer visualization of tissues and its abnormalities, thereby allowing clinicians or healthcare researchers to provide more informed decision regarding the patient care or understanding the interaction between different objects at a very minute scale. Again, like other domains, biological studies involve a quantitative analysis. So what do I mean by quantitative analysis? Such that, for example, in case of bone, a conventional CT having a relatively higher slice thickness can only provide so much detail about the internal structures or the cortical trabecular bone intricacies of the bone. Therefore, the quantitative nature, that is the percentage of porosities, its shape, the direction, the structural intricacies, cannot be completely understandable from a conventional CTs. While using micro CTs, it can be measured, the size, the shape, the structural intricacies of specific structures. Like I said, bone can be measured. You That can be done using quantitative analysis. So there are software's algorithm that are solely developed based on microcity based imaging that can provide quantitative data regarding the structural details of the different aspects of bones. So higher resolution here can provide more accurate quantification, leading to more reliable as well as reproducible research results. Or in some other cases, researchers or clinicians may need to integrate or what we call image registration, that is register multiple images at different time points or images of same structure or a same organ tissue using different imaging modalities to extract more information from it. This sort of image registration sometimes is of utmost importance when we try to understand the growth of a certain, let's suppose a tumor or a bone growth after introducing a typical design of biomaterials inside the living system. So here, this high resolution of micro-CT can provide, facilitate an accurate alignment whereby stacking those images at different time frame or from different imaging modalities can be useful for comparing and understanding the effect in a very comprehensive way, or to understand the changes in the internal structures in a very detailed manner. Again, coming to typical biomedical related applications, one of the major applications or one of the important area where micro-CT is very important is in the domain of tissue engineering, where first and the important thing is the scaffold characterization. Now, the scaffold being a very delicate and a very small structure, so characterization of scaffold, including its percentage of porosity, the surface roughness, the strut thickness, that can be easily done without causing any damage to the scaffold using micro-CT based imaging as well as post-processing. Also, small laboratory animals like rodents, when they are used to perform some preclinical studies, like I said, image registration for those rodents in given, let's suppose, a certain pharmaceutical or an implant can be done in vivo without cause sacrificing those uh, laboratory animals in order to perform tissue characterization, including, for example, assessments like bone growth, bone turnover, as a function of time, which is again called a 4D micro-CT data, or sometimes the growth of a tumor or effect of a certain pharmaceutical, release of drug of a certain pharmaceutical. So in vivo uh, characterization, in vivo tissue characterization of small laboratory animals without sacrificing them for a longer period of time can provide useful information which was otherwise difficult to get using conventional CT. Also, ex vivo characterization of human tissues can also be performed. And the next thing, in case of biomedical applications or the areas, that is particularly regarding the bone or the bone related studies, typically to investigate different indexing parameters of bone, for example, the volume fraction, the porosity content, the microstructural features like trabecular orientation, the mineral densities, etc. They can be calculated through the micro CT based images, as well as one of the important domain of micro CT application, we can say, is the computational biomechanics, where the micro CT data can be used, the resolution micro CT data can be used to produce a discrete representation of the cortical or a cancellous bone, or the interaction between soft tissues and bones, which can facilitate the understanding of how a foreign object, for example, an implant, can interact with the bone or the bone surrounding soft tissues to a greater extent. So, as to understand why is micro-CT so important, here are two important application of micro-CT. So, first one is that this is the diaphysis of a femur. So, we can calculate the bone anisotropy from the micro-CT based data. So, this gives the bone anisotropy, where the blue one essentially means a value of normal anisotropy to be 0, while the red one gives a highest anisotropy level of 1. So here we can actually calculate, we can actually measure this from a CT scan, micro CT data. And on the other side of the spectrum, this is a very unique one, micro CT data. So this is a candy uh, uh, that has been scanned using micro CT, and it has revealed different compositions that contained inside that candy. So this gives the extent of or the array of applications that the micro CT can perform, and the array of information that the micro CT can extract from a object, albeit that the object cannot be very larger in structure, so they can comparatively smaller one. So What are the advantages of micro CT, particularly when we consider the conventional CT? So first thing is that the first one should remember that the micro CT are, are the one that are relatively smaller device as compared to conventional CT, which are quite big and cumbersome process. Uh, but micro CT are relatively smaller as this has more industrial application. Therefore, the micro CT image can be obtained of from small objects or specimen, unlike conventional CT. Having said that, there are certain advantages of micro CT that are very important for research related purposes. The first thing being the high spatial resolution. So, as I already talked, micro CT provides significantly higher spatial resolution as compared to conventional CT, which makes it suitable for imaging smaller structure with minute structural intricacies and objects at a very finer scale. Like I said in the previous slide, the bone as well as the candy, they're very small structure, but at that small scale, even for that, the leaf that I showed in the initial slides, that has a very small and a very thin, delicate structure, yet the veins and all the internal details can be easily seen through the micro CT. Therefore, this higher spatial resolution is of crucial importance for detailed examination for biological tissues, small organisms, as well as new materials. The second one, the second advantage is the non-destructive nature. So, although CT can be called a non-destructive imaging technique, but the application of micro CT is much vast as compared to CT in terms of both biological, both research related, biomedical, materials related, as well as industrial application. So micro CT can be non-destructively image the internal aspects of biological specimens or any other materials, allowing researchers to study the internal structure without altering or damaging them. This is particularly important while considering the delicate biological samples or any other valuable artifacts where preservation is very essential. And again, another important one being the small FOV, field of view. Since micro-3D systems typically have a very smaller FOV, field of view, as compared to conventional 3D, so this initially it might be termed as a limitation when going to the CT, which can image larger structures, but it is very advanced when focusing on small localized areas of interest and thereby providing greater detail and clarity. Again, finer anatomical details like I discussed previously, micro CT, its small field of view, its higher small pixel size, its higher resolution, superior resolution provides excellent capability of capturing finer anatomical details like the one seen in case of cortical and cancellous bone with detailed structure in the cancellous geometry, which is otherwise impossible to capture using conventional CT. This is advantages again in biological research where these intricate features can be useful to understand at the cellular or even subcellular level. Again, another important is the radiation exposure since it's a very small and compact device. So the micro CT is optimized for imaging small objects and therefore it typically requires less radiation as compared to conventional CT. And again, micro CT has comparatively higher temporal resolution, allowing for faster image acquisition. Therefore, it's beneficial to capture dynamic processes in real time, like the flow of blood or any flow of fluid through a porous media or changes in tissue morphology over time. small period of time. Having said that, both micro CT as well as CT have their share of mm, advantage, the resolution, non-destructiveness, contrast sensitivity, a very special application. CT can be used in case of clinical settings to capture images, internal images of a larger area. Therefore, the choice depends on the specific requirement. But when it comes to micro CT, the application is vast, particularly in the domain of biomedical research or mineral science related research. So, so far, the key features of a micro CT based system: higher spatial resolution, as we've already discussed, allowing researchers to visualize internal structure at a very finer scale. It is non-destructive. Therefore, unlike traditional histological methods, when we consider biological or tissue-related imaging, which often this histological methods, they often involve slicing or cutting or staining the sample, thereby destroying the sample. Or in case of preclinical research, microCT can be used into study animal models for several purposes like drug development or any other disease research to understand the bone turnover after implantation of a prototype implant. Thereby, it enables researcher to monitor the changes in anatomy or any other aspects like bone dead. The sacrifice, and it also has other ancillary implications like porosity measurement to understand the distribution of pores, to understand to distinguish between different composite material, etc. To briefly talk about the working principle of microCT, it's essentially the same as a conventional CT. So there is a X-ray source that is there, and there is a detector. So we can see this is the X-ray source and this is the detector. So conventional tomography techniques, the source and the detector that they rotate. But in this case, the source and the detector are stationary, while there is a podium, there is a place where the sample is held and that rotates, thereby taking different images at different angles. So it involves the use of X-rays again. So the basic principle of microCT is involve the use of X-rays to create the cross-sectional images or the cross-sectional slices of an object. The object here is rotated while the X-ray projections are taken from various angles. These projections are then reconstructed using detailed, a very specific 3D reconstruction algorithm to provide a 3D representation of the structure that contain detailed internal intricate structural intricacies. So here we can see this is the X-ray generator, this is the detector, and this is the podium, like I said, and the podium rotates, and thereby the X-ray slices are taken at different angles. So this is the first projection after several of the images at several angles have been taken. This many slices can be created, and they are formed, they stacked upon each other to finally create this image of this tooth, as we can see here. So to better understand this thing, so as we can see the X-ray from the understanding of conventional CT, the X-ray travels through the sample, which is placed between the detector and the source, and the attenuated beams that are there, the beams that pass through the sample are recorded by the detector. The sample here, in case of microCT, is then rotated by a certain degree, and another projection is captured. This procedure is done until the entire 180-degree or 360-degree rotation is done. So this is the first projection image that that captured from the sample. After that, since when all the projections images are captured, they are processed using computer to generate what is known as cross-sectional images or reconstruction images. So here we can see this is the reconstruction image that is generated from all the projection based image after the sample has rotated 180-degree or 360-degree. And finally, specialized softwares are used to reconstruct these images, these projection or cross-sectional images, to provide a maneuverable 3D volume rendering, and which is useful for further analysis. So to sum it up, there is the X-ray source and the detector are kept fixed, while the sample that is placed between the detector and the source at a certain podium that rotates at a certain degree, and a projection image is taken or recorded at the detector is. While this procedure is followed for a complete 180 or 360 degrees, these projection images are then processed to form the cross-sectional image of that structure at a certain plane. And finally, these cross-sectional images are reconstructed using specialized computer-based algorithms to model 3D volume rendering, which is useful for further analysis. So to further understand what the different image processing techniques that are used in case of microcomputer tomography to understand, to visualize the internal structures. So the first thing is that the resolution that is provided by the micro-CT machine is either is almost nearly isotropic, that provide that there is no necessity to confine the presentation of the images to the traditional axis format. So what does it mean? Essentially that one need not need to capture the image at a certain plane or a certain axis, because the resolution is isotropic and the software can generate all the different images at all the different planes. Instead, yes, the thing. So a software can construct the volume by arranging individual slices in a stacked manner. So a single image at a single plane is sufficient to construct the 3D volume of that object by the means of software, and subsequently the program has the capability to showcase the volume in an alternative representation, that is basically the volume rendering, which shows the external as well as the internal intricacy. There are several highly powerful, capable image reconstruction softwares available, both proprietary as well as open source, which can process these micro-CT data. These data are generally captured in the form of what is known as a DICOM format. So these DICOM format data are captured and they are processed using these image processing softwares, image reconstruction softwares, to provide this 3D volume rendering and further processing. For example, generation of CAD models, for computational simulations, for generation of 3D printable objects, is or what is commonly known as STL files for 3D printing. And then the important thing that I was talking about is the volume rendering, which is a method that is to present a 2D projection of a discretely sampled 3D data that is generated by a micro-CT scanner. So essentially, it produces the 3D data from the 2D projection that can be that are obtained through the micro-CT scanner. Typically, these scans follow a consistent pattern, such as acquiring one size per millimeter, and they commonly exhibit a uniform arrangement of pixels. So this volume rendering is useful before performing the 3D image segmentation, because this they have a volume regular pixel, I mean the image image matrix, where each volume element or voxel is denoted by a singular value or the CT number derived from sampling the surrounding image of the voxel. So here this specialized technique produces a detailed understanding, detailed rendering of the volume from 2G projection. If different structures have similar threshold density, the next then it becomes impossible. For example, if there is bone and another ceramic object that is present, so they have similar threshold density or radio density. So it sometimes become impossible to separate them by adjusting the volume rendering parameters. So from the 2D projection image, the software cannot distinguish between the both. So the solution, the process through which this separation can be performed is known as segmentation, which is again a very important tool, which is again a very important tool to uh, image segment, I mean, to separate out different images in microcity. This segmentation can be manual or automatic, and they can be used to remove unwanted structures or to separate out commonly common structures having common threshold densities. So coming to the application of this microcity, which is the most important thing to talk about here. So for the biomedical applications, as I've already discussed, the primary one is the bone imaging, and there are several areas where this microcity can be used when coming to the bone imaging related biomedical applications. So that can be used to determine the mineral density as well as the bone morphology. So here microcity is widely used to study the bone density, the bone microstructure, or bone morphologies. So there are several more indexing parameters present that solely depends on the microcity related data that helps researchers to evaluate, to understand the bone structure, investigate the deterioration or the bone turnover quantitatively, or to evaluate the effects of treatment on the health. Again, for orthopedic research, microcity employed to assess different joint structures, to study the cartilage bone interface, implant interaction, as well as to study the efficacy of implants as well as prosthesis. So here we can see this is a few of the images. So here we can see using micro-CT data, this is a part of the bone where the bone growth can be seen here. As we can see progressively, the bone growth can be seen here. So this is again the 4D application of bone, that is the time specific application of bone. Uh, sorry, the micro-CT. So it signifies that the bone growth can be seen using the micro-CT device for a very certain period of time. Here also we can see this is the internal structure of a long bone. So the cortical shows the cortical as well as the cancellous bone structure with very finer detail, which I was talking about previously, that micro-CT having a very higher spatial resolution that is given by the micron level pixel size is very useful for understanding, for visualizing the structural intricacies. So here we can see what does it mean actually. So here we can distinguish between the surface roughness as well as the cortical and the cancellous bone. Thereby, if virtual implantation scenarios need to be studied, need to be simulated, it will be useful to study how the implant and the cancellous as well as the cortical bone interact. Here also it can be seen through specialized algorithm. This is the what is known as the thickness of the cancellous bone has been shown here. So this is again a specific application of micro-CT where specialized algorithms are used to study these structures, to study the morphological indices of these trabecular bones. Then again, another important area where micro-CT has been used significantly is the in case of dental research. So obviously for dental research, there are two very specific applications. One is to study the morphology of the tooth or the jaw bones to understand the dent or to investigate the dental structure, the tooth and the surrounding tissue. So it helps in understanding the tooth morphology, any other dental diseases. Well, another one being the dental implant or the dental prosthesis studies. So micro-CT can be used to assess the integration or what is known as a osseointegration of different dental implants or prostheses, and it can be seen what are the effects of the implant design parameters on the surrounding bone based on this micro-CT study in a computational simulated environment. See here we can see this is a typical micro-CT showing the surrounding bone as well as the tooth. Here we can see the internal structure of the tooth and its interaction with the surrounding bone. So we can also visualize this thing, the, the root canals and all other internal structure as well as the dentin and everything. So this is useful to understand the internal detailing of the micro-CT, I mean the dental tooth. And this is the one where we can see this is a dental implant placed at a bone. This is a preclinical study that I was talking about. So it shows this yellow color is essentially basically the bone formation around the implant. This is the implant and this yellow is the bone formation. So here bone, it can be seen that different material, what are the response towards osseointegration or new bone formation. So this is visualized using micro-CT, and based on the segmentation method that I described previously, the implant and the bone can be separated out and can be color coded differently for better visualization. But this one is again the application of micro-CT and its high spatial resolution, that this is the dental implant and this is a bone. This is particularly the trabecular bone that can be seen here. So it is useful to understand what these threads of the implant in how they interact with the surrounding bone. So since the micro-CT provides a detailed structure of the surrounding trabecular bone, it is very useful to study their interaction with the interaction of the dental implant threads with the surrounding bone, and how altering any of these structures, let's suppose the pitch of the thread, the depth of the thread, as well as the density of the surrounding bone, the bone mass, how they interact the overall performance of the biomechanical performance of this system. So again, these are the very few examples that I show here, but there are several other examples available how dental area is benefited by the application of micro-CT. The next thing is that when it coming to the imaging of small animals, so these studies, like I said, small animals, if any implant, for example, if a dental implant is placed in an animal, and the purpose is to see how the plant or the generally previously those animals were sacrificed to study to see the histological sectioning of those implants to see the bone growth in the structure. But with the advancement in microcity, now a temporal data can be obtained, a time specific data can be obtained where this bone growth or the bone turnover can be seen for different time periods. That is again another application of the non-destructive examination of the anatomical feature like the bone growth, as well as there are other features as well to understand, to visualize non-destructively, like organ structure or any effect of drug or treatment modification. So here we can see this is basically comprises of all different things that I spoke about previously. It involves, so this is the tail of a mouse where a certain implant was placed, and the idea was to see how bone growth was happening. So basically, this involves the image registration and segmentation technique that I previously spoke about. So this one means the new bone formation, whereas this color means the bone resorption or the erosion of bone. So this is the clinical setting or at the laboratory setting, and this is what is predicted using the computational setting or through computational simulation. So both the data are identical, they were captured from data. So due to this irregular or detailed trabecular arrangement, it can be seen that the prediction of the computational system is comparatively accurate with predicting the overall performance or the bone formation structure. So again, this has been done over a period of time for that animal without sacrificing the animal, thereby capturing the bone remodeling phenomena. And like I said previously, the biomechanics or rather the computational biomechanics application of microcity to understand the joint mechanics by providing detailed images of the joint and their structures, as well as different muscle or ligaments that are attached and how they interact during a certain activity, as well as for computational modeling that can be used to model bone interaction at a they are useful for predicting bone remodeling as already shown or the in a computationally simulated environment. And another application here, a very important one, also apart from the biomedical or biological application, are in the domain of material science, where micro-CT can be used, are used rather, to study the porosity analysis, to study the percentage of porosity, or to study the composite material or their structural intricacies, for studying the concrete and bending material and how their interface, the interplay between them at the interface, as well as to study biomaterial scaffolds. So here we can see this is a scaffold-like structure, a porous structure. So we can easily understand, we can easily visualize the porosity here, as well as all the struts, all the other structure here. So we can calculate the percentage of porosity or the volume fraction from it, as well as we can measure the average strut thickness. The same thing can be seen here as well. So this is a very unique application of microcity or computer to say So computed tomography, microcity is a very unique application of computed tomography to understand to the internal structures of the mind at a very finer scale at with a very greater detail. So this brings the conclusion of this lecture. Thank you for your participation. For any clarification, please write to me. Have a good day.